So we'll start off today. I want to look at this one. Find the missing angle A here for me quick. So what do we know about this one? Okay, that's one thing we know, that in any triangle, the angles have to add up to 180 degrees. What else do we know on this particular triangle?
That angle A and the other missing angle have to be the same.
Okay, why do those two have to be the same?
Because it's
There you go. These two sides are the same length. Those two angles have to be the same. So how does that help us find angle A?
subtract the known angle from 180.
Okay, so 180 degrees minus the 42, 18, 44 gives us
50 minutes, 30.
hold on. I was going to say you skipped a step there. That's your total, yeah. So here, I'll go through it here. So this is 179. This will become 60. Borrow to make it 59. That's 60. So you get 16, 41, and 137, right? Looking right? And then what do we have to do to that? Divide it by 2. So 2 goes into 137. That's 68 times. That's 136. So that's 61 degree becomes 60 minutes. So 101 divided by 2 is 50, which is 100. That gives us 1, or 60 seconds. So 76 seconds, or 38 seconds. So 68 degrees, 50 minutes, 38 seconds. Sound right? How many came up with that? Cool. Now on this one over here, once again, you're told it's an isosceles triangle. We're given these two angles. I want to know angles A and B. First of all, what can you tell me about angle A right off the bat? How do you know it's 90 degrees? Okay, yeah. If we have an isosceles triangle, if we bisect the angle between the two equal sides, and that's what we did here, we created two equal angles, then that line that we used has to do 3 things. It bisects the angle, it also forms an altitude, which means it forms a right angle with the opposite side. That's how we got that right angle. And it splits that opposite side into 2 equal pieces. So it's what we call a median to the other side. And the opposite is true. If we draw a line from that angle that's between the 2 equal sides, and it forms an altitude, well, then it has to bisect the angle and divide it into the opposite side into 2 equal pieces. So once we know that that's 90 degrees, this angle down here is pretty easy to find. It is going to be what? 27, 26. Perfect. You can always take a shortcut with a right triangle. You know the angle sum has to be 180. But when you have one that's 90, you know that leaves you with 90 degrees left over to get to 180. So instead of working with 180, you can just work with 90 in the one single angle. And yeah, you can go from there. Okay, one last one I want you to look at. I want you to find angle A in this mess. Assume, by the way, these 2 lines are parallel and these 2 lines are parallel. So on this one, as I said, there are a lot of different ways to approach it. Since we have 2 sets of parallel lines here, there are a lot of different angles that have to be equal. Like this angle here that we're looking for has to be equal to this one, and this one, and this one. So if we found any of those 4, we'd be okay. In fact, it's also equal to this one, and this one, and this one. And that one. Or we could approach it as finding angle A directly. Since we already have this angle here, what else would we need to know? Well, we'd either need to know this one, then the 3 of them would add up to a straight line, or 180 degrees. Or we need to know this one, and the 3 of those would add up to a straight line, or 180 degrees. Well, both of those angles are going to be the same anyway. So how do we find it? Yeah, the 64 degrees 12 minutes down here has to be the same as this angle here because those are corresponding angles. So 64 degrees 12 minutes. It's just confusing because you got all those extra lines in there. It's hard to see where the parallel lines are. Now we have those three that have to add up to 180. So I'll take the 6412 and the 5137 and add them together. So 115 degrees 49, and what do I do with that? Subtract it from 180. So I'm going to get 11 minutes and 179, 64 degrees, 11 minutes. What do y'all think? 1 minute off?
I can show the way I did it just because I thought it was.
Yeah, go ahead.
With 64 and 12 minutes.
Yep.
That's a triangle of its own. Well,
Right in here, yep.
Just directly across from the bisecting line. It's
Right here.
exactly the same.
Yep.
So I just took the 6412 and 5137, subtracted it from 180, and made that A
Had to be that angle. Yeah. Exactly. Yeah. And you could even done it right here. You know that A has to be equal to this angle there. So since it's a right a triangle, they have to add up to 180.
I figured that was a little easier for some people probably.
Yep. And it all depends on who you are. Some people see triangles, some people see parallel lines. There's, like I said, there's probably a dozen or more ways to go about this one. So good. Very good. Here's one that's a little bit different speed for you. Okay, so I've got the angles there. I'm going to fill in. We have 40 inches, 68 inches, and 79 inches are the lengths of the three sides. So I'm going to label them sides A, B, and C. Can I tell which side goes with which? Or which of those numbers goes where? Okay, what do you mean?
40 is A.
40 is my smallest side. You said it has to be A. Why? It's across from the smallest angle. Very good. The smaller that angle is, the smaller the opposite side has to be. When we go to label triangles, technically the way we would label them is we would label them with small letters on the sides. This would be little a, little b, and little c. Then the angles would be capital A, capital B, and capital C. And you'll see what happens is big A and little a, big A being the angle, little a being the side, are the ones that correspond to each other because side little a is the side that is affected. Its size is affected by the size of angle A. So the smallest side has to be opposite the smallest angle. What else do we know then? B would be 79. It is opposite the largest angle, so it has to be the largest side. And then, of course, C being in the middle has to be the remaining 68 inches. With that, I think you guys are ready for your... Well, time to look at new stuff then. So we've been talking about the triangles and polygons and stuff. Now to make the transition into trig, it may seem a little awkward, but we have to talk about circles. So when we look at circles, there are a lot of parts of a circle that we already know. Of course, the distance from the center of the circle out to the edge of the circle is called what? The radius. Now here's one we may not know. If we have a line segment that connects 2 points on the circle, can anybody tell me what that's called? It is called a chord. Very good. A chord that happens to go through the center of the circle is called a diameter. Which brings us to our first relationship in a circle. The diameter is equal to 2 times the radius. Next, as we keep discussing parts of this circle, ones that we already know, the distance around the circle is called the circumference. Very good. And the circumference, of course, is equal to either pi times the diameter or 2 times pi times the radius, because 2 times the radius is the diameter. Some that we may not already know. A line, well, we've talked about this one a little bit, actually. A line that just touches the edge of the circle, but doesn't actually cut into the circle, is called tangent. Very good. Tangent means to touch. A line that actually does cut through the circle, like this, is called a secant line. Secant. It cuts through the circle. Some vocabulary we touched on a little bit last semester, but we'll review. If I have 2 radii of a circle, it cuts out this little pi wedge. That pi wedge is called a sector. A segment is if you have a chord. The segment is that little piece that's between the chord and the outside edge. That's a segment. Now we said the whole distance around a circle is the circumference, but if we're just dealing with a piece of it, like from here to here, that is called an arc. Now we talked about arc length and sector area and stuff like that last semester. We will review it quickly here once we get done with all of our vocabulary junk here. This angle right here that is formed is called a central angle. Anybody want to guess why it's called a central angle? Because its vertex is at the center. Very good. We could have an angle like this. It is called an inscribed angle. Inscribed means to be on, or the vertex is on, vertices on. So that angle is inscribed on the circle because its vertex is on the circle. Going to be some very important relationships between central angles and inscribed angles as we go through the next few days. An inscribed polygon. If we said that there was a square inscribed in a circle, which is something that comes up for you guys if you have a piece of round stock, you need to create a piece of square stock. So a square inscribed in a circle looks like that. Each of the vertices of the square, each corner of the square is on the circle. It's inscribed. Of course, now with the vocabulary we have, not only can we have the central angle and the inscribed angle, we can have this type of angle. What are those 2 lines called again? That cut through the circle? No, chord is just from here to here. The whole line is a secant. Very good. So this is a secant angle. Bless you. It's formed by 2 secants. Bless you again. And then, of course, we can have angles like this. They're not inscribed. They're not at the center. Those are simply what we would call, bless you again, interior angles. Because they're on the interior of our circle. Like I said, over the next couple days, there's all sorts of rules and relationships. We're going to learn about those. For now, got a little bit more vocabulary to go. Bless you. You okay? First of all, hey, cats. So anyway, so if we have a circle, we've talked about the diameter of a circle, but we're going to talk about something called a reference diameter. The reference diameter of a circle is literally the horizontal diameter. If you think about it as a compass, we talked about navigation, we were talking about angles. It is the diameter that goes from east to west across the center of our scope there. The reason it's called a reference diameter, you'll see very clearly when we get into trig, is that's where angles are measured from, what we call reference angles. But for now, all we're going to look at is that horizontal diameter and another feature of a circle that's defined off of it. The word sine is something all of us have heard. You've probably heard the sine bar brought up. Probably even seen a basic trig function of a sine working with the sine bar, finding angles and stuff like that. Richard, I'm sure, showed you a little bit of it. The word sine actually is not a trig function. It's become a trig function now, but where it came from was a feature of the circle. A sine is created using that reference diameter. If you pick any point on the circle, the sine of that point is the distance to the reference diameter. Now remember, distance between a point and a line is always measured at a perpendicular, at a right angle. So you draw the line, a line from that point to that reference diameter, forming a right angle with the reference diameter. The length of that segment is the sine of that point. So obviously that point has a larger sine than this point does. This point has a smaller sine because it's closer to the reference diameter. Whereas this point here has a slightly larger sine because it's slightly further away from the reference diameter. Does that make sense? And you're probably starting to sit there wondering, okay, you know sine's a trig function. How on earth does this relate to the trig functions? We'll connect it in the next couple weeks. So now let's go back to reviewing some of our calculations with a circle. So if I have a circle with a radius of 4 millimeters. Review from last semester, I want you guys quickly find the circumference. So what do we use to find the circumference?
Pi times diameter.
Yep. So diameter in this case would be 8, right? Yeah. So pi times 8 is going to be, what, 25.12 millimeters approximately? 1.3 if you use the pi button. It's 1.2 if you use 3.14. Yep. Next, I'll have you find the area of this circle. So area is found by pi times radius squared. So it'll be times 4 squared. Depends again. If you use 3.14, it's 50.24. If you use the pi key, it's 50.27. So anywhere in that range would be acceptable on a quiz or a test. Not always. In this case, it turned out to be the area is double the circumference, but it's not always like that. For example, I can give you this one, Cody. So let's say we have a diameter of 10 inches. Find the circumference in the area. I'll give you guys a couple minutes. No problem. So you get a circumference, 31.42. That's just 10 times pi times 10, or 3.1415 times 10. Area comes out to be almost exactly 78.5 inches squared. This should have been millimeters squared up here, by the way. I don't know why I left that off. You guys come up with those numbers?
Circumference is pi times diameter?
Yep, so this one's just pi times 10. And then this one's pi, this one's pi times 5 squared. So now that we've explored all these, let's take a look now. If I go to this circle here, and I cut out a sector. and I want to find its area. I need to know either the radius or the diameter of the circle, but what else do I need to know? I need to know this angle here. I need to know the central angle. Very good. If I know that central angle is 60 degrees, I can find the area of that sector. Because I know that the whole circle is 78.5. And that is 360 degrees. Correct? So then, what would the area of just a 60-degree piece be? Well, I can cross multiply and divide to get about 13.1 square inches approximately. 13.08333, whatever. What do you think? That's not so bad? Now there's a shortcut that's often used rather than setting it up in a proportion like that and cross multiplying and dividing. What they do is they take the area of the whole circle. That little A with that circle symbol means the area of the whole circle. Times what I just put up there, that is the Greek letter theta. You know how we use X, Y, Z, A, B, C letters as variables for missing sides, lengths of sides? We often use Greek letters for missing angles. So that is the symbol we use, or the variable we use to represent an angle over 360 degrees. So what this is telling us is to just take the area of the whole circle times the central angle for that sector divided by 360. This is telling us what fraction of the circle. 63/60, this is what fraction of the whole circle we have. And you'd end up with that same answer if we did that, just doing 78.5 times 60 over 360. So let's have you try it. Pretend that's in the center of the circle. So this is 110 degrees, 7 millimeter radius. So our first step is always to find what? Area of the whole circle, which will be pi times 7 squared. So in this case, I'm just going to use 3.14 times 7 squared is 49. 153.86, does that sound right? Millimeters squared. That's the whole circle. Now to find the sector, this little A with the pi wedge by it is the symbol for area of a sector. It's that 153.86 times 110 over 360. .01 degree, or 47.01 millimeters squared. 03, that's, you use the pi key instead of the 3.14. That's perfect. It doesn't really matter. I do my answer keys both ways. Well, keeping that knowledge in mind, what if I asked you to find the length of that arc? What do you think we would do? Well, following the pattern of what we just did up here with the sector area, there we found the area of the whole circle and used the fraction. Here we're going to find the circumference of the whole circle, which is going to be pi times 20. Where'd 20 come from? The diameter is 10-inch radius, 20-inch diameter. So that's going to be 62.8 inches. Then what? Yeah, to find the length of that arc, the arc length, 62.8 times 50 over 360. 8.722. 8.72 inches. Not bad? Let's see how you're doing on your logical thinking today. So I have a circle here. This chord happens to be 12 inches long. Cutting an arc out here between its endpoints. It happens to be 13 inches long. If I come over here and I create a chord, 12 inches long. Can you figure out the length of this arc? 13 inches, very good. It takes a second to realize it, but yeah, those two arcs have to be equal. If they are in the same circle and they have chords that are the same length, the distance around there must be the same. There's no way it can be any different. In fact, not only if they're in the same circle, but if they're in two circles that have the same radius or same diameter. Let's say that this is 6 inches in radius and 6 inches in radius. Well, if I have an 8-inch chord and an 8-inch chord, this arc and this arc have to be the same. This one goes straight back to our formula. This is a 40-degree central angle. This is a 40-degree central angle. And if I tell you that this arc here is 7.2 millimeters, what's this arc here have to be? 7.2 millimeters. Because that arc is a fraction of the whole circle, and the fraction is based on that central angle, if they have the same central angle, same arc. Good. This is going to tie our circle stuff back in with our triangle stuff that we just did on Tuesday. So I'll make this one a little bigger. I'm going to put a chord out here. And what I'm going to do is I'm going to take a radius here that goes through that chord. But this radius hits the chord at a right angle. It's perpendicular to the chord. Believe it or not, this allows us to say a lot of things about that chord. Now, looking at it right now, it doesn't seem really obvious. But if I do this, I draw in this radius here, and this radius here. In this, I'm going to put the chord in blue as well. What type of a triangle did I just form there? Isosceles. How do we know it's isosceles? Yeah, those two sides are both radii of the circle, and the radii has to be equal to another, a radius has to be equal to another radius in the same circle. That's an isosceles triangle. And one of the big things we went over on Tuesday, and we actually reviewed at the beginning of today, is in an isosceles triangle, when you draw a line from that vertex between the two equal sides, if it hits the opposite side at a right angle, it's an altitude, right? And if it does that, first of all, it cuts this angle into two equal pieces. And it cuts this side into two equal pieces. And the opposite's true. If we draw in a line that cuts this side here into two equal pieces, it has to be perpendicular. That's going to be huge for us as we do calculations with pieces for machining. Because let's say you have a shaft that is going to have a flat surface milled into it for a keyway or whatever you want to do with it. To locate that, it's much easier if we find its center using those rules. So we know that's going to have to come out there at a right angle. We can find the distance from the center up to that surface, knowing that length it has to be. And we know whatever the full length is, we can divide it by 2 to get the right triangles. Let's see, there's a couple others I want to put out there. We've covered this one a little bit too, but we've never said it formally. If I have a line that's tangent to a circle and a radius that comes off that plane of tangency, what do we know about the relationship? They form a right angle. They're perpendicular. We've discussed that. Continuing on with that, if I have two tangents that come out here and intersect, Because of that relationship, of course, we know that this is perpendicular here, and this is perpendicular here. We also know that this length and this length are the same, don't we? Well, if I draw a line across here, obviously I can draw this through here. That's going to form a right angle. What's that? We're running a little short of time today, so I'm not going to keep going with the proof of this. We'll show you more of it next week if we need to. But the result is the length from this point of tangency out to where the two tangents intersect here ends up being the same as the length from this point of tangency to where they intersect. So that allows us to create an isosceles triangle there and a lot of things that we're going to do with our circle. Last thing I want to show you, then we'll give you the homework and we'll discuss this more on Tuesday or on Monday. If we have two chords within a circle, they intersect each other, and you can see they cut each other into two pieces. So this chord is cut into 12 millimeters and 3 millimeters. This chord over here, this piece is 4 millimeters. Excuse me, I can find this other piece because and we went over this briefly last semester when we talked about arcs and stuff like that, arches. The product of the two pieces has to be the same for both chords. So 12 times 3, that's the two pieces in this chord, has to equal 4 times whatever this piece is. That's going to come out to be what? 9, yes. 12 times 3 is 36. Divide by 4, x equals 9. We'll cover that more next week. For now, your homework is in your packet. I believe it's still in this packet. Double check for me, make sure the pages are in there. Page 305 through 306. We're looking at 1 through 26. Should be able to get away with just doing the odds to be enough practice, but if you're struggling, go ahead and do the evens as well.